Welcome to Hartman Math. We're going to look at a library of parent functions today. Prior to that, go ahead and pause the video here, work through warm-up problems 1, 2, 3. For number 1, you're going to answer parts A and B. All right, what we should get for part A is that f of 1 is 4, because you're using the top part of the definition. Since the input 1 is less than or equal to 1, we could substitute in that part of the definition of the function, and we get the absolute value of 4 is 4. Part B, f of 2 is 3, because 2, the input, fits this condition. So we're going to substitute in there, and we're going to get the square root of 9, and we get 3. Number 2, the function is even. Remember, when we're checking algebraically, we're going to do, in this case, g of the opposite of x, negative x. You need this step here where we're replacing all of the x's with negative x. Since the absolute value of a negative is the absolute value of a positive, it just becomes the absolute value of x here. Since when you square a negative, you get a positive, it does not influence this at all. So we keep the minus, this becomes positive x squared, and that is g of x. You need to have this step. You need to show this step here. And we conclude that since it's the same as the original function, that it's even. And then as a difference function problem, I keep seeing this over and over, must be important for f of x equals 2x squared minus 3x plus 1. The difference quotient would be 4x plus 2h minus 3, where h cannot equal 0. So if it was close, see if you can rework that. Otherwise, ask a question during class time. So we're taking a look at 1.6, a library of parent functions. Begins with example 1, writing a linear function. Write the linear function for which f of negative 2 is 5 and f of 4 is equal to negative 4. So x comma y, x comma y, we're given 2 points. And when we're given 2 points, we're going to want to see if we can come up with the slope, as it is a linear function. So slope going first, y2 minus y1 is over x2 minus x1. Slope formula, we would get negative 9 over 6. We would reduce it to be negative 3 over 2. We found the slope. Now, we do not know the y-intercept, not the y-intercept, not the y-intercept, because x was not 0. So these are just random points, so probably want to use point-slope form for the equation of a line. So y minus y1 is equal to m times x minus x1. So you could pick either the first point or the second point. It will not matter. So I'm choosing this one. So y minus 5 is equal to our slope that we just found times the quantity, parentheses, x minus the negative 2, which does simplify there. Distribute, pretty easy one to distribute there. When I distribute there, here, and then negative 3 over 2 times positive 2 is negative 3. And then to finish it off, we do want to get the y by itself. So add 5 to both sides. Box your answer. Final answer, we've written the linear function. So a couple special types of linear functions. We've got f of x equals c. So that would be like f of x equals 5, f of x equals negative 2. And as they're showing in the figure, that's going to be a horizontal line. Slope is 0. F of x equals x is another pretty important one for a lot of people coming up through Math 1. Pretty challenging one to graph if we think of that as y equals x. It does have a y-intercept of 0 and a slope of 1, up 1, right 1. So it is completely diagonal, cutting exactly halfway through quadrants 1 and 3. Some other ones that we should have a lot of experience, going back to Math 2, more practice than Math 3, f of x equals x squared, U-shaped, parabola is what we would describe the shape, and some different characteristics. The domain is the set of all real numbers, or you could put parentheses, negative infinity, comma, positive infinity, if we like the interval notation, as it does go forever left, and it does go forever right, as we could kind of imagine that there are arrows on those as well. The range is not unlimited like that because it doesn't go down forever. It only has positive y values. So we would say that the range is non-negative real numbers, or y is greater than or equal to 0, or bracket 0, comma, positive infinity. The function is even because it's symmetric about the y-axis. It has an intercept at 0, comma 0. That would act as both an x-intercept and a y-intercept. It is decreasing until it hits here. So we could say from negative infinity to 0. Remember, we always use parentheses for increasing and decreasing and constant. And then it's going up over here. So starting at 0 and going to infinity, meaning always from 0 beyond, is it's going to go up, so therefore increasing. Because it's even as symmetric about the y-axis. A relative minimum means on a small window, what's the lowest it could go? Well, if we kind of just look in this area here, the lowest that it possibly goes is 0, comma 0. So there's a minimum of 0 at 0. And that's the very common f of x equals x squared, or they will say squaring function. So taking a look at cubic, square root, reciprocal functions, starting with the cubic function. Again, that's going to go back to math 3 on that one, where you've dealt with the x cubed function or the cubic function, where it's going to look like this with some key points. If you remember from math 3, if we looked at the tall graph there, it was 0, 0, 1, comma 1, and then 2, comma 8, since 2 cubed is 8. And then over here, negative 1, comma negative 1, negative 2, comma negative 8, and it does keep going. So that does create the shape. Since we can substitute any x in, it goes forever to the right and forever to the left. The domain is the set of all real numbers, or parentheses, negative infinity, comma positive infinity. The range is also unlimited. It goes up forever, goes down forever. So all real numbers, or again, negative infinity to positive infinity in parentheses. This function is odd. If we put a finger down there on the origin there and we spun the graph halfway around, it would look exactly the way it did now, because this then lays over here and this part flips up to over there. It would look exactly the same and therefore be odd. It has an x and a y-intercept at 0, 0. It's always increasing, always going up, so increasing throughout the domain. And it is symmetric with respect to the origin, which we already kind of talked about because that kind of defines what odd would be in terms of a graph. Square root, you've had some experience here. Key points being 0, comma 0, 1, comma 1, 4, comma 2 are usually the three primary key points that you have to be aware of. The domain is the set of all non-negative real numbers, meaning 0 and positives. So we might say x is greater than or equal to 0, or more likely you would say, in terms of interval notation, bracket 0, comma positive infinity. Starts at 0, goes to the right. The range is actually kind of the same. Y is greater than or equal to 0, or once again, bracket 0, comma infinity, because it starts at 0, close point, hence the bracket, and it goes up forever. It has an x and a y-intercept at 0, comma 0, and it's increasing throughout the domain. Remember, for increasing, we never use brackets, so parentheses 0, comma infinity. It's neither odd nor even. It has no symmetry that matches symmetric about the y-axis or point symmetry. If we spun it, we go from quadrant 1 to quadrant 3, and that's a change. So it does not have that kind of symmetry. The reciprocal function, this might be a new one, f of x equals 1 over x. Looks like that. It's in quadrants 1 and 3. The domain of the function is basically everything except for 0. So from negative infinity to 0, that takes care of this part. And from 0 to infinity takes care of that part. And then range up and down ends up being the same. Negative infinity to 0, 0 to infinity, thinking up and down. It is odd because if we spin it halfway around, this ends up over there, and this part ends up over there. It doesn't touch an x-axis or a y-axis, so has no intercepts. It is decreasing over here, and it is decreasing over here. So it has those two parts where it's decreasing in both of those parts. And we already talked about, since it's odd, it's going to be symmetric with respect to the origin. Step and piecewise defined functions. So this one is the greatest integer function. You don't have to really know a whole lot about it, but look at the notation. It's kind of the double brackets, and they do connect here. So that's what's going to kind of denote the greatest integer function. So we're talking about the greatest integer that is less than or equal to, and that's key, less than or equal to the value of the number. So the greatest integer function of -1 is what integer is the integer that's closest, that's less than or equal to that value. Well, since that's an integer, that will be the value. So anytime that you're evaluating this at an integer, you will get that value. However, when we look at -1/2, we're talking about the greatest integer that is less than or equal to -1/2. -1/2 is not an integer, so we're going to have to drop down to the next one below that, and that would be -1. So same thing here, the greatest integer function of 1/10 would be the greatest integer less than or equal to 1/10, and that would be 0. So that's why we've got these little parts here where, according to the definition, it's going to have a closed point over here because the greatest integer function of 0 is 0, since 0 is less than or equal to 0. And then at like 1/10 is right there, and 0.75 is right there. It'd still be 0, which is why the y-coordinate here is 0. And then it does not include 1 as 1 jumps up and is defined over here. So open circle on the right, closed circle on the left. The domain is still the set of all real numbers. We can take the greatest integer of any real number, but the range is only going to be integers, 0, 1, 2, 3, 4, 5, because we're talking about defining it to be in terms of an integer. The y-intercept is 0, 0. X-intercepts all throughout here, so could be, there's one at 0, 0. There's one at 0.5, 0, 0.7, 0, etc. The graph is constant between those pairs and the open circle and the closed circle, and it jumps 1 unit each time. Okay. So evaluating a step function, we've just looked at the greatest integer function, f of x, where if we're talking about this, we've slightly adjusted it here, the greatest integer of x plus 4, and let's look at a couple different values here. So basically 3 different problems. We're substituting in -3/2 into here. So the first thing we do, -3/2 plus 4. So that would be -3/2 plus 8/2. That would be 5/2. That is not an integer. So what is the greatest integer that's less than or equal to 5/2 or 2.5? You got to go down to the next one, and that would be 2. Let's try 1. F of 1. Plug in a 1. We will get the greatest integer of 5, and that is an integer. So the answer's got to be that same integer. Okay. And lastly, -4.05. F of -4.05. Greatest integer of -4.05 plus 4. Go ahead and do the adding first. You get the greatest integer of -0.05, which is not an integer, so we now need to move down to the next lower integer. and that's going to be -1. Graphing a piecewise defined function, sketch the graph of f of x, and we've looked at evaluating these, we haven't graphed them yet. So the first thing we're going to do is we're going to take a look at this part here. We're going to look at what we're graphing here as a function. Kind of looks like an mx plus b situation. So we're going to be graphing a line, and here's where pencils might be really useful. We're going to identify the y-intercept of +2 in that case, right there, and then a slope of -1/2, down 1, right 2. So we can kind of think about this line that would pass through there. But the thing is, the condition says we don't want the entire line. We only want the part of the line that has an x-coordinate that is less than or equal to -2. So where is that along this line if we were to continue it along? And one strategy is just to draw the whole thing and then just start erasing. So I might do that here. So if I use that strategy, then I'm talking about, okay, I only want x values that are less than or equal to -2. Where is the x-coordinate -2? That's right here. It does say or equal to, so I'm going to use a closed point there. It did not. If it just said less than, I would use an open point. And I only want the ones going this way. So I can get rid of the rest of it because it doesn't satisfy the condition. Now let's look at the other part, which you might recognize as a parabola, x squared minus 3. If we look back previously, we looked at the squaring function that's been shifted down 3, so parabola. Something like that would be our parabola, and it does say x values that are greater than -2. Here's an x-coordinate of -2. It does not have the or equal to, so I do need to turn this into an open point there and just have going to the right from there. And that would be the piecewise. So just graph each, and if we do it in pencil, then you can erase the part that does not satisfy the condition. Go ahead and pause the video here and see if you can work out the checkpoint to get the graph of f of x is equal to, and here's our piecewise definition. And what it should look like is for the part x is less than 3, here's the x-coordinate of 3. It does not have the or equal to, so an open point, and going left from there with a y-intercept of -1 and a slope of up to right 3. And then this is also a line, so that part over there, that's kind of interesting. In this case, at the value of 3, where we kind of had split it, they actually had the same value. And this would be a closed point. And it turns out that a closed point would fill in the open point and say there is a point right there, and it does count. And just a summary, this last thing we're going to look at, just all the different parent functions that we've kind of been looking at. We didn't discuss this one today, it did not come up, but this one comes back from Math 2 and Math 3, the absolute value of x, which turned out to be the v with linear parts to it. But the other ones, the constant function, which was horizontal, f of x equals x, the linear one was just x, so that was the one that was kind of completely diagonal. We just discussed the square root function, squaring function, the cubic function, The new one, the reciprocal function, and the step or greatest integer functions. There are other step ones, but this is specifically the greatest integer function. That's it for today. We will see you next time.